In the following 3 videos, I believe, maybe it's 4, we're going to look at higher ordered differential equations. In particular, we're going to look at homogeneous equations, and in this video, we're going to look at constant coefficients. The good news is this is very similar to what you've already learned for second order differential equations. It's just kind of more of everything. So we will start with the nth order linear differential equation, where we have a constant times y to the nth derivative plus another constant times y to the n minus 1th derivative, all the way down to a n minus 1 times y. And again, our a naught, a1, everything in front of the y's, they're real constants. And as I said, we start very similar like we did when we were looking at second order differential equations. We assume that we have a solution of the form y equals e to the rt. So now our differential equation is e to the rt a naught times r to the n plus a1 r to the n minus 1 on down to an. And this is just like second order differential equations. And now we have our characteristic equation, which is this polynomial here. And we set it equal to 0 for the homogeneous differential equation, and we solve, and we look for roots. And since it's the nth, if we're in nth order linear differential equations, we're looking for n roots. Some will be repeated, and some will be complex. So we have our 3 cases, just like second order. We have real unique roots, and we have a very similar form of the solution. We have complex roots, and one thing to remember about complex roots, they always come in pairs because it's plus or minus I mu, and then we have the cosine mu of t and sine mu of t. So if you have a third order differential equation, it's possible you have 2 complex roots, but you're never going to have just 1 or just 3. And then last, we have repeated roots. Using the same sort of strategy, you're going to multiply your e to the rt times t, or it might be t squared, or to the s minus 1. And we'll do examples of all of these. And then also the last point is, so you may have forgotten how to find roots of these polynomials to the nth degree, since the last time you did it was probably middle school or something. And so to remind you how you did this in middle school is if r was a root of this polynomial and r was rational, so we're going to assume it's of the form p over q, where p and q have no common factors, it's in lowest form, then p must be a factor of an, and q, which is on the bottom, must be a factor of a naught. And that will give you some possibilities to try out. And this some notes, this process will not find complex roots, but if you can divide out the real roots, you can reduce the polynomial, and then hopefully it's easier to work with. And to compute cube roots, fourth roots, or higher roots of a complex number, we're going to use Euler's formula. So it's good to remember e to the it is equal to cosine of t plus I sine of t. And we will start with an example, and we'll start with real unique roots. So here we have y to the 4th plus y to the 3rd minus 7y second derivative minus y derivative plus 6y equals 0. And we have y0 equals 1, y prime of 0 is equal to 0, y double prime of 0 is equal to negative 2, and y triple prime of 0 is equal to negative 1. Like the second order differential equation, we assume the form of the solution is y equals e to the rt, and then we have the similar characteristic equation. Here we have r to the 4th, r to the 3rd minus 7r, since it's double prime squared, minus r plus 6 equals 0. This has these 4 roots here, and I'll show you how I found these roots on the next, after we solve the entire problem, which means that our general solution is going to be y equals c1 e to the 1t plus c2 e to the minus t plus c3 e to the 2t plus c4 e to the minus 3t. Again, totally analogous to the second order equation. To solve the initial value problem, we do have 3 derivatives now to take, but first I plugged in y of 0 is equal to 1. So when we plug in 0, we get c1, c2, c3, c4 is equal to 1. I calculated y prime, I plugged in 0, and I'll get, plugging in 0, I have c1 minus c2 plus 2c3 minus 3c4 is equal to, according to our initial condition, is 0. Our y double prime will give us c1 plus c2 plus 4c3 plus 9c4 equals negative 2. And then y triple prime is equal to c1 minus c2 plus 8c3 minus 27c4 equals minus 1 when you plug in 0 for t. And solving these four equations, we get c1 is equal to 11/8, c2 is equal to 5/12, c3 is equal to minus 2/3, and c4 is equal to minus 1/8, which means y is equal to 1/8 e to the t plus 5/2 e to the minus t plus 2/3 e to the 2t minus 1/8 e to the minus 3/2, and this is the solution graphed. And this is it. This is our solution. As I had mentioned, on my next slide, I'll go over how I found the roots of the characteristic equation. Our characteristic equation is r to the fourth plus r to the third minus 7r squared minus r plus 6 equals 0. And as I had noted on our overview slide, if the root is rational, in other words, it's p over q, where p and q are integers having no common factors, then p must be a factor of a naught, this 6 here, and q must be a factor of a4, which would be the 1. So q is equal to plus or minus 1, and p is equal to plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. So there's 8 possibilities, right, of matching p's and q's together, which is not too hard. We can start with some of the small numbers. R equals 1, we can plug that in. That would be 1 plus 1, that's 2, minus 7 minus 1, that's minus 8 plus 6. So that would give us 0. So R1 is one solution. You can plug in R minus 1, and you'll see that's also a solution. You'll see 2 and minus 3 are solutions. So n equals 4, and there are 4 solutions, 4 roots. So that should be it. Our next example is an example of complex roots. And what you want to remember, if r is equal to lambda plus or minus I mu, that this is a pair, right? Because it's plus or minus. So you have a pair of roots. So you want to remember complex roots come in pairs. Our example is y, fourth derivative of y minus y equals 0. We have y of 0 is equal to 7/2, y prime of 0 is equal to minus 4, y double prime of 0 is equal to 5/2, and y triple prime of 0 is equal to minus 2. We start again with the assumption that y is of the form e to the rt, and we look at the characteristic equation, which is r to the fourth minus 1 equals 0. When we factor r to the fourth minus 1, we can factor that to r squared minus 1 times r squared plus 1. This over here, r squared minus 1, gives us r as plus or minus 1. This r squared will give us r is equal to plus or minus I. Therefore, the solution to our equation is c1 e to the t plus, that comes from this r1, c2 equals c2 times e to the negative t, that comes from r is equal to negative 1, plus, and from r is equal to I, we get c3 cosine of t plus c4 sine of t. Using our initial conditions, y0 is equal to 7/2, so I plug in 0, and I get c1, c2, this goes away, and this becomes c3 equals 7/2. I take the first derivative, and I plug in 0, and I use my initial condition to get this equation. Similarly for y double prime and y triple prime, and my initial conditions give me c1 is equal to 0, c2 is equal to 3, c3 is equal to 1/2, and c4 is equal to minus 1. Therefore, y is equal to 3 e to the minus t plus 1/2 cosine of t minus sine of t. This next example is repeated roots. Y to the fourth derivative plus 2y double prime plus y equals 0. And this one we have for a characteristic equation, r to the fourth plus 2r plus 1 equals, and that's r squared plus 1 squared, which is r plus I squared, r minus I squared. So let's look at the r plus I. That will give us c1 cosine t plus c2 sine t, and because it's squared, so we have repeated roots, we need to multiply one of our solutions by t. So that'll give us c3t cosine t plus c4t sine of t, and those are our 4 solutions corresponding to our 4 roots. Our next example will cover this point. If we need to compute cube, fourth, or higher roots of a complex number, we're going to use Euler's formula, e to the it is equal to cosine t plus I sine of t. Our example problem is y to the fourth plus y equals 0. The corresponding characteristic equation is r to the fourth plus 1 equals 0, which is the same as r to the fourth is equal to negative 1. So that involves finding the fourth root of negative 1. And negative 1 expressed as a complex number is negative 1 plus 0i. I express it this way so we can look at this in the complex plane. So when we represent a complex number, we need two coordinates. We need a coordinate to represent the real part and a coordinate to represent the imaginary part. So we do that in the complex plane where the x-axis is our real portion and then the y-axis is our imaginary portion. So here we're saying that x is equal to negative 1, which is over here, and then the y value is 0. So this expressed in the form of an exponent, the radius r in front of the e is 1 because we're out here at 1, and the angle from here, it's always measured in the counterclockwise direction, is pi. So negative 1 expressed as an exponent is e to the pi I. This is the general form of how you would convert an imaginary number or complex number a plus bi into an exponent. It's equal to r e to the I theta, where r, if you plot out a plus bi in the complex plane, a is your coordinate, your x coordinate on the real number line, b is your y coordinate, that's the I axis. So then your r is your radius when you have your vector ab, which is square root of a squared plus b squared, and theta is the inverse tangent of b over a. So then this is exactly what a plus bi is equal to in the complex plane. I'm not sure why this wasn't so much covered in your textbook, but it seems like you need to know it. And by the way, these the r and the theta, you should think of this as plotting your complex number in the complex plane, where x is the real number, y is the I-axis, and then this r and theta are your polar coordinates. So it's a plus ib in polar coordinates. So I put this general formula over here, your other example, and I have 3 more examples to go over. I have a couple of other coordinate conversions for you just so you can get used to this writing a complex number in terms of e. So if our complex number is equal to I, so in other words, the real part is 0, and I is multiplied by 1. So here we are in the I, on the y-axis, we go up 1 unit. In the x-axis, the the real part is 0, so this is it here. So we have a length of 1, which gets multiplied here, times pi over 2 is our angle going from the real axis equals 0. In a counterclockwise direction, we have e to the pi over 2i. If we have 1 plus 2i, so that's 1 on the real axis and 2 on the complex axis, on the y-axis. And then the length of our vector here is equal to square root of 1 plus 2 squared, which is square root of 5. So that's our radius, r. And then our angle here is the inverse tangent of 2 over 1, or inverse tangent of 2. So 1 plus 2i is equal to square root of 5, e to the inverse tangent of 2 times I. One more example. If we have 1 plus I, so that's 1 on the real axis, and then 1 on the complex axis, so that gives us this vector here, that's this point here, our 1, 1 point. So the length of our vector is square root of 2, and the angle is pi over 4, so that's square root of 2 e to the pi over 4i. And back to our equation, we have negative 1, and we express that as e to the pi I, which is also equal to cosine of pi plus I sine of pi. And then also, this is true because when you come around 2 pi, you get back to your negative 1, so we want to express that as cosine pi plus 2m, where m is any integer, pi plus I sine pi plus 2m pi, which is e to the I pi plus 2m pi. Now, if I want to take the fourth root of negative 1, I take the fourth root of e to the I pi plus 2m pi. Here I have e to the I times pi over 4 plus m pi over 2. So that's going to give me cosine pi over 4 plus m pi over 2 plus I sine pi over 4 plus m pi over 2. So this is my fourth root of negative 1. I take what I just said back. So this is our expression for the fourth root, but we want to find 4 roots, so we're going to set m equal to 0, 1, 2, and 3. So when we set m equals to 0, we get cosine of pi over 4 plus I sine pi over 4, which is square root of 2 over 2 plus I square root of 2 over 2, which you can write as square root of 2 plus square root of 2I over 2. I would have left it this way, but your book simplified it or wrote the equivalent expression 1 plus I over square root of 2. M equals 1 is fairly straightforward. Plugging in m equals 1, you get cosine of 3 pi over 4 plus I sine pi 3 pi over 4, which is negative square root of 2 over 2 plus I square root of 2 over 2, which is this expression here, negative 1 plus I over square root of 2. For m equals 2, so cosine of 5 pi over 4. So it's the same value as pi over 4, except you have to remember at cosine at 5 pi over 4, and cosine is in black, right? It starts at 1, and by 2 pi it's back at 1. So at pi over 4, it's negative. So I'm going to have my negative square root of 2 over 2. Sine, also, this is in black, at pi over 4 is also negative. So it's the same value as pi over 4, but it's negative. So I have my negative square root of 2 over 2. So this corresponds to this third value. And then m equals 3, I'll let you calculate on your own. But it should come out to this fourth value here. Now that we have our 4 roots, we can look at our solution, which is of the form y equals e to the rt. And one other thing I should mention. Here, these two are the complex conjugate pairs. Here's the complex conjugate pairs. And just like we did for second order differential equation, we use the two solutions from one of the two pairs. So we're going to use these two. So first we have e to the rt. That's e to the 1 plus I over square root of 2 times t. I rewrote this as 1 over square root of 2 plus I over square root of 2 times t. Now I'm going to use this part of my formula. If the root is equal to a real part plus I times an imaginary part, then our solution is e to the real part times t times cosine the imaginary part times t. And also the second solution is e to the real part times t sine of the real part times t. So here we are. E to the real part is 1/2 t. And then the imaginary part, so we have cosine of 1 over square root of 2 times t, plus I, and then 1 over square root times t. And remember, if I sine of t is a solution, then you can get rid of the I, because sine of t is also a solution. So this expression here, is the solution associated with our first root. Similarly, for our second root, we get this expression here, and this is our final answer. Because, yeah, we were just looking for the general solution, no initial conditions. One more example, because I wanted to give an example with different types of roots. So find the general solution of 4y triple prime plus y prime plus 5y equals 0. Our corresponding characteristic equation is 4r cubed plus r plus 5 equals 0. So if the root is of a real nature and it's this p over q, then p has to be a factor of 5. So it's either plus or minus 1 or plus or minus 5. Q needs to be a factor of 4. So it's plus or minus 2, plus or minus 1. And I'm going to start with the smaller numbers. So I'm going to try r equals minus 1. And I plug it in, and I find it equals 0. So r equals minus 1 is my first root. And it is a real root. Now, instead of plugging in all the other numbers, because actually I know that there are no other real roots, I am going to divide my polynomial, 4r cubed plus 0r squared plus r plus 5, by my r plus 1. So here I have my polynomial, my what is this called? The divisor. Okay. So here to get a 4r cubed, I need to multiply by 4r squared. So multiplying 4r squared by r, I get 4r cubed multiplying by 1, I get plus 4r squared. I subtract this from this whole polynomial here. This becomes 0. I get a minus 4r squared, and I bring down my next term, which is r. So to get rid of the 4r squared, since I have an r here, it's minus 4r. So minus 4r times r is minus 4r squared, times 1 is minus 4r. Subtracting this here, I get minus 5r, bringing down the 5, I get 5. And fortunately, I can just add a 5 here. And that's the end of my division. One thing about this division, since you know it's going to divide evenly because we already found that this is a root, it's pretty easy multiplication usually. It's not a horrendous division. But here, this is r plus 1 times 4r squared minus 4r plus 5 are how I can factor this polynomial. And now that this polynomial is a quadratic, I can plug it into the quadratic equation, and I get my other complex roots are 1/2 plus or minus I, which means my general solution, first I have my real root, minus 1, is c1e to the minus t. And now my complex portion is e to the 1/2, right, because 1/2 is the real part of my complex, 1/2 t times cosine, and then there's a 1 in front of this I, so that's the imaginary part, cosine of t plus c3 sine of t. So this is the general solution. To review what we've looked at, we looked at nth order, linear, homogeneous differential equations, and we borrowed so many methods from our second order linear differential equations. In fact, we borrowed all of our techniques and we just expanded on them. First, we looked at our characteristic equation, and we realized we would either have real, complex, or repeated roots, just like for our second order differential equation. For real, we do the same thing. We have c1e to the r1t, c2e to the r2t, up to cn e to the rnt. For complex roots, very similar. When we have a complex root, our solutions are e to the lambda t, lambda being the real part of our r, cosine of omega, omega being the imaginary or what gets multiplied by I in our r of t, and our second solution is e to the lambda t sine mu of t. And note that complex roots always come in pairs. Then we had repeated roots, and say r has multiplicity of s, then we're going to have e to the rt, and just like we did for our second order, then our next solution would be t e to the rt. But now, of course, we can have third order, so if it's third order, the next one, and it's a root of multiplicity 3, then our next solution is t squared e to the rt, and we keep adding a factor of t until we run out the multiplicities. Next, we looked at finding roots of polynomials, and if we assume that there are real roots, in other words, r is rational and is equal to p over q, we said that p must be a factor of our an term and q must be a factor of our a naught term, and then we would just test all the possibilities into the equation and see which ones solve the equation. This should be equal to 0. So again, this process will not find complex roots, but you can always divide out the real roots to reduce the polynomial and then see if there are complex roots. And to compute cube roots, fourth roots, or higher roots, we used Euler's formula here, which is e to the it is equal to cosine t plus I sine of t. And that's it for this video. Thank you for watching.